Welcome back to class 24. Here's another example. This is taken out of Borgnacki's 10th edition, I believe. That might be the same out of the earlier editions as well. So we have a room at 22 degrees Celsius, and it's heated electrically. We haven't done much with electrical heating as examples in this course. At least I haven't. With a 1500 watts to keep a steady temperature. The outside ambient is 5 degrees Celsius. And we want to find the flux, the entropy flux into the room, air, and into the ambient, and we want the rate of entropy generation. Okay, so let's proceed. And we said that okay, so if we wanted to make sure we're understanding what the process is, let's draw a little picture. And we could say we have a control volume drawn around the house, and we have an electrical heater. And he's got a plug, and I made him go outside for whatever reason he got plugged outside. So we're going to have a rate of electricity. That's supposed to be EL. It doesn't look like EL, does it? No, EL? EL. Okay. Well, electricity coming out, but we're also going to be losing Q out of these things. Now, if we did the conservation of energy, and across this control mass, we said E. Now, our convention is usually that heat rate in is positive, but this is out, so this is going to be negative out. And we usually our convention for the conservation of energy, to say coefficient conservation of energy, we have the power out is going to be a negative, so this is power in, so it's positive. But we don't have anything else in our system right here, so it just turns out that they're going to be equal to each other, which we probably could have just figured out on our own. But here we've done a little bit better, and see, I still made the thing in cursive. So there's taking care of the conservation of energy equation. Let's go ahead and do the entropy. Some people say conservation of entropy. I don't like that because we're generating entropy, so it's not really a truth. They just call it the entropy equation. We're accounting for the energy, so maybe entropy anyway. So that's going to be equal to the summation of the Q over T plus the rate of the generation. So the question is, what temperature to use, right, for this thing? We have 22 degrees inside, and we have 5 degrees. Well, it's passing over this boundary, and this is the temperature on the outside, and I think that's the best way to kind of like think of it, like what temperature to use. This is not factoring into the entropy because it's not a heat change onto the thing. We'll see in a second what happens here. So as part of this right here, we're going to have 0 equals, and of course this is a negative rate, so it would be negative Q dot out over T ambient. I didn't give it a thing right here. That's going to be plus S gen. So the S dot gen, what we're left with, is simply going to be 1500 watts divided by our temperature of 5 degrees. We have 5 plus 273, and we end up with 5.396 watts per degree Kelvin. All right, so I wrote down here, why 5 and not 22? And I wrote for that because 5 degrees Celsius is on the outside of the control volume through which the heat passes, right? So this is everywhere right here, but just as it crosses this, it has to go past the 5 degrees Celsius. So that's where the entropy generation occurs. before it, before it moves through this thing, it hasn't had to generate any entropy. It's the act of generate going across this boundary to the 5 degrees Celsius. But if we were to, if we look at the heater, make a control volume. Here's a little heater, and of course here's our plug. Make a control volume across this. Now we have this Q coming right to here. This is the Q out now. From here, it's the same heat, right? Same heat being pumped out of this and coming back in there, but we're using electrical resistance, which we could classify as a work, right? So we're still putting our W back in there, work in, compared into there. So we have the S dot gen, because of this running thing right here, is going to be that 1500. And now we're going to use the 22 plus 273, and equals the 5.085 watts per degree Kelvin. And so right here, this thing has generated entropy, right? It has generated the entropy as we're going through it. Now, if you were to, so let's see if I'm going to say this the right way. No, I think I'm going to stop with right there. So we've identified, here's an entropy generation, and here, but here's the one that they want, the rate of entropy generation for this. Actually, let me go back. I'm hemming and hawing because I don't want to say the wrong thing, but I do believe. Oh, come on! Sometimes I just can't believe how difficult life has to be. I can't get my what do you call it to work? Yeah, my I'll get the PDF to come up. Let's see. This is problem 100. All right, let's see what it says right now. I was hemming and hawing because I wasn't 100% sure I wanted to say this, but so the entropy generation is the 5.393. It's just pretty close to it in my head. I said, comment, the flux of S into the outside air is what leaves the control volume, and since the control volume did not receive any S, it was all made in the process. Notice most of the generation of this was done in the heater, right? The room heat loss process generates very little. Okay, so yeah, that's what I wanted to say. That if you go ahead and you take a look here, this right here is actually in part because of this, right? So this thing has actually generated this entropy flow, and that entropy flow is seen right here. So let's go on to the next example.